Hello, welcome to lesson 4.3. Today we're moving on from graphing. We're going to be talking about factoring. Specifically, factoring, we're going to start with problems where a equals 1. When a is not 1, these get more complicated, so we're going to handle that in a separate lesson. Today, a is going to be 1. Remember, that's the number in front of the x squared. Specifically today, we're going to talk about basic factoring. I like to call that one unfoiling. We're going to use our information about how to FOIL in order to predict the factors, or we're going to go backwards to figure out what got multiplied. We're also going to learn some special products, that is patterns that we should recognize to make factoring easier. Then we're going to use factoring to solve equations. And lastly, we're going to find the zeros of quadratic functions, which is a process very similar to solving equations. So we're going to talk about factoring, and we're going to use that to solve equations or find zeros. As far as basic factoring, it all stems from our information about how to FOIL. So if you remember FOIL, that's where we know the correct order to multiply just to make sure we get everything. We do first, in this case, x squared, and then outside, which is in this case negative 7x. Inside gives us 4x, and the last two gives us negative 28. Most of the time, the outers and inners will be like terms and get added together. So what we're looking at when we see a trinomial is generally a first term, a last term, and then two terms that have been added together. That is the sum of the outers and inners. And that's an important understanding, because if we're looking at the product, that is a trinomial, this is the result of a multiplication problem, and we're trying to find the factors, which is why it's called factoring. We're looking for the factors that got multiplied together to make this. Knowing that what we're looking at is the first term, a last term, and then the sum of outers and inners makes our job a lot easier. Because the fact that the first piece here, x squared, is a product of the first two parts of our binomials means they're going to be x and x, because that's what makes x squared. Similarly, if we look at the last one, we know the last two have to multiply to negative 6. In order to multiply to negative 6, we're going to need 1 and negative 6, or 2 and negative 3, or 3 and negative 2, or 6 and negative 1. There's 4 different sets of numbers that will multiply to negative 6 here. And basically we can consult the outers and inners to pick which pair is going to work to make this trinomial. So if we look at this, the outers and inners for x plus 1, x minus 6 would be negative 6x and positive 1x, which makes negative 5x. If we do this one, that's negative 3x and positive 2x, which makes negative 1x. Here we've got negative 2x and positive 3x, which makes positive 1. And then negative 1 and positive 6 makes positive 5. Comparing that with the original trinomial lets me know that positive 1 is the correct outer and inner sum. So my correct factorization will be x plus 3 times x minus 2. Basically, you're looking for two numbers that multiply to negative 6 and add to positive 1, because that's what we're looking at when we see a trinomial, is the end is a product and the middle is a sum. So multiply to negative 6, add to positive 1, and that's why 3 and negative 2 are the correct answers here. If we try this again with a different trinomial, notice we've got x squared plus 14x plus 48. 48 is the product of our two numbers, and 14 is the sum. That is, we need two numbers that multiply to 48 and add to 14. So if I make a list of all the factors of 48, that's 1 and 48, 2 and 24, 3 and 16, 4 and 12, and 6 and 8. Those are all going to multiply to 48. Since the 48 here is positive, we don't need negatives. They're all positives. They could both be negative, but since they need to add to a positive number, I'm pretty sure we're looking for positives. Looking down the list, that's 49, 26, 19, 16, and 14 if you add them. And since 14 is what we're looking for, 6 and 8 are the ones that are going to add to 14. So I factor this as x plus 6 times x plus 8. Notice if you FOIL this, you get x squared plus 8x and 6x, which makes 14x, plus 48. So this is the correct factorization. Here in our third example, x squared minus 9x minus 5. The factors to make negative 5 are going to be, that should be negative 1 and positive 5, or positive 1 and negative 5, but neither of those is going to add up to negative 9, so this one actually cannot be factored. None of the factors are going to add up to negative 9, so this cannot be factored. We call that prime. Make sure you try all the factors. 5 is nice, it's prime, so there's only 2 factors. But if this were a composite number like 36, there's a number of different pairs of factors you need to try before you can be sure it can't be factored. If you're looking to start a problem and you learn to recognize the special products, it can really save you a lot of time in the long run. So that there's 2 special products that we're going to look at today. The first one is called difference of squares. Notice here we've got a square, a squared, and we have another square, b squared, and there's a subtraction between them. Difference means subtraction, so this is called the difference of squares because you're subtracting 2 squares. This has a very predictable factorization. You basically find the square roots of the front and the back, and you put them twice each, once with minus and once with plus. And this works out every time. So in this second example here, x squared minus 9, notice x squared is a square, and 9 is 3 squared. So I use x and 3, once minus, once plus. X minus 3, x plus 3. Notice this is similar to what we did before, but the middle term is the one that's missing. The b is 0, which means my 2 numbers have to be, in fact, opposites in order to add up to 0. So we get x squared and 3x and negative 3x, and the last term then is negative 9, so the 3x and the negative 3x cancel. A perfect square trinomial is a different pattern. It's a little more complicated. Notice we have a square on the front and on the back again, but instead of just a subtraction in the middle, there's a middle term that's 2 times the square roots of a squared and b squared. So 2 times a times b. The middle term can be positive or negative, but the last term has to be positive. B squared is always going to be positive, because even if b were negative, when you squared it, you get a positive. The factorization for this is a plus b, that is the square roots, and it's squared. Notice the sign is going to be the same as the middle sign. The b squared is always positive. So for example, x squared plus 10x plus 25, notice the square on the front, x squared, the square on the back, 5 squared is 25, and then in the middle I should have 2 times x times 5. So 2 times x times 5 is 10x, so this one's a perfect square, and that means b is 5 and a is x. So x plus 5 squared. If you were to FOIL this times itself, you'd get x squared and 5x, which makes 10x, and then 25 on the end, 5 times 5. So make sure you check the middle. Don't just assume it works because the front and back are squares. Once we have factoring down, we can solve equations using factoring. This whole thing is based on the zero product property, which is a rule or an understanding that basically states if you multiply 2 things together, that is if the product of 2 expressions is 0, so you multiply 2 things together and you get 0, one or both of the expressions must be 0. So anytime you multiply 2 things together and the answer is 0, one of the things you multiplied was 0, even if you didn't realize it. So in this case, if I have 2 factors and the product is 0, that is I multiply them together and I get 0, then one of them has to be 0 to make this true. There's no number you can stick in that will work unless it makes one of those 2 factors 0. This makes our job a lot easier because we just need to figure out which makes each of these factors 0. So we just take them into 2 separate equations and set them each equal to 0. So if x plus 3 equals 0, or x minus 2 equals 0, and those are both easy to solve. You subtract 3 over here, you add 2 over here, you get x is negative 3 or x is 2. And those are the numbers that are going to work. If you stick in negative 3, notice this one becomes 0, and 0 times negative 5 is 0. If you stick in the 2, you get 5 times 0, which is 0 again. So these are the numbers that are going to make this equation true. Notice we took the factors and made up 2 separate equations where we set each factor equal to 0, and that gave us our 2 answers. Let's try another example. 3x equals x squared minus 40. Notice it's not equal to 0 already. I must make it equal to 0. In this case, I'll subtract the 3x from both sides. So I get 0 equals x squared minus 3x minus 40. Has to have 0 on the other side in order to use the zero product property. So my factoring, the original one is not going to help me because it's not equal to 0. Have to get 0 in order to split it up. So let's see, x squared minus 3x minus 40. Numbers that multiply to negative 40 are like 1 and negative 40, 2 and negative 20, 4 and negative 10, also 5 and 8, which are the ones that are going to be 3 apart. So in this case, I need negative 8 and positive 5. They're going to multiply to negative 40, and they're going to add to negative 3. So when I set these equal to 0 individually, I get x minus 8 equals 0, or x plus 5 is 0, which gives me x equals 8, or x equals negative 5. When I'm finding the zeros of quadratic functions, it's very similar. A 0 for a function is just the value you stick in that's going to give you the answer 0. So this is exactly the same as solving for this if the y were 0. So we're going to do it the same way. We're going to factor, and then we're going to use the zero product property. So x squared minus 4x plus 4, in this case I recognize the back is a square. This is 2 squared. The front is a square. That's x squared. So I'm looking at 2 and x, and if I do 2 times 2 times x, I get 4x. So this is a perfect square trinomial. Since the middle is subtraction, I'm going to keep subtraction. Notice x and 2 is the square root of 4, so x minus 2 squared. In this case, then, I don't really need to set up two equations because they'd be the same. X minus 2 equals 0, but that means x is 2. In this example, x squared plus 10x plus 16, the front is a square and the back is a square, but the square root here is 4, and if I do 2 times 4, I get 8, not 10. So this is not a perfect square trinomial. The middle doesn't work. I need two numbers that multiply to 16 that add to 10, which will be 8 and 2. So x plus 8, x plus 2. They multiply to 16, they add to 10. Setting these equal to 0 individually, I'm going to get x is negative 8 and x is negative 2. So those are going to be the zeros for this function. Those are the numbers that when I stick in, I get zeros. On the graph, that means they're going to be the intercepts. Remember, we saw this form here, this factored form. We called it intercept form. Negative 8 and negative 2 are the x-intercepts of this function. It's the same thing as a 0. It's an x-intercept. So what we did today, we talked about factoring by unfoiling. Remember, you're looking for the numbers that multiply to c and add to b. We also talked about a couple special products, the difference of squares and a perfect square trinomial, both of which, if you remember the rule, you can factor pretty quickly. You solve equations by factoring and then set each factor equal to 0. Remember, you have to have a 0 on the other side or the whole thing breaks down. And then you find the zeros of quadratic functions the same way that you solve equations. I hope you enjoyed this.